Thank you very much, everyone. Thanks for coming. Getting kind of halfway through the conference now. Hopefully you're all into the swing of it. My name is Jeremy Kerr. I work for the IBM OzLabs group, and one of the things we do is getting Linux working on fancy new IBM hardware. Part of that is kernel, part of it is firmware, there's all sorts of bits involved. One of them is a bootloader. So, going to give a bit of background about bootloaders, what's involved, what we're doing, and what Petitboot itself does. So you have three kind of things that we want out of a bootloader. We want to load our OS into memory somehow, so typically pulling it off disk or net or some weird device. We want to transfer our execution into the OS that we've loaded, and possibly give a bit of interaction to allow the users or administrators to control how that boot process works. So maybe you want to select between different boot options or different operating systems, or change the arguments you're going to give to that option to change the behaviour of the system. So three kind of important things that we want our bootloader to do. Typically, if you're familiar with the grub bootloader, kind of I guess it's one of the standard cases of a bootloader for Linux. In this case, we're talking to some PC BIOS firmware. Now, PC BIOS is getting a bit old and being replaced by EFI now. So I'm going to kind of base most of my examples on what's sort of the current state of things with EFI. So in this case, we've got grub talking to the firmware. And the firmware in this case is sort of helping out the bootloader as an abstraction layer. So in this case, our bootloader has requested a read from the firmware. Firmware has a little disk driver which performs the right commands to talk to the disk. To read a sector off the disk, data is returned to disk driver, and then the firmware returns that to the bootloader. So in this case, we're kind of using or including some of the functionality that firmware gives us in our bootloader process. And typically that will be, this read example will be to load our kernel into memory. So in this case, grub has used the firmware interface provided by this UEFI firmware. This interface here, we're using the read disk API, loading our Linux kernel, and then finally passing the execution to the Linux kernel. So now the kernel is running. It's doing the usual boot stuff, so initializing our hardware, setting up all the kernel data structures, that sort of thing, drawing penguins on the screen. And one of the other things we'll do is we'll instantiate its own disk driver. So we'll have this driver we use to then issue ATA commands to the disk and do the kind of things you expect an OS to do in terms of reading and writing to the disk and whatnot. So here we kind of see a bit of a quirk. We have two driver implementations. We have one in firmware and one in the kernel. Now, not necessarily a problem. I mean, it's only a disk driver. It's not a huge amount of code. And I guess one of the quirks is that when we're doing bring up, we may have to write a driver twice. So once for the kernel for this one, and then once when we need our firmware to support that driver to boot from. But again, like I said, it's not a huge problem if we have a duplicated driver. It's only a small part of code. The problem sort of comes when we start to get other functionality into it. Say you want to boot from net. We'll have a network card in the device. We also need a network driver to drive that. We're using a network driver. We probably need some way to sort of abstract the low-level network bits. So we'll have a TCP/IP network stack. UEFI can support booting over TFTP, so we need something that supports TCP for that. And then perhaps, well, actually, sorry, in this case we've got a TCP driver in the firmware, but that API doesn't quite suit how grub likes to boot. So grub actually ignores the network stack in the firmware and uses its own little UDP-based driver for TFTP loads off the network. We also probably want some user interaction from our firmware, so we might need a GPU driver as well, just to display our bootloader or firmware screens on an actual monitor. And we probably also want some input, so here we need a USB driver as well to handle your mashing on the keyboard and telling it to stop booting. We might want sort of more advanced block devices, so we'll have a SCSI layer for that that handle things like the LUNs and the targets and whatnot. We're getting, since we've got a SCSI layer and a network layer, why don't we add some iSCSI as well? That's supported by there's an EFI protocol for doing iSCSI boot. Now we've got a few devices, maybe we'll want some sort of PCI layer to handle our handle the bridges and the targets and whatnot. Probably also want some way to automatically configure our network. So we'll have a DHCP clients in there to handle the auto configuration. I'll probably also want to actually make use of the data we read off the disk. So we'll want a file system here. So we could go on all day adding stuff and thinking about all these weird boot configurations and whatnot. But this is kind of, I guess, a sensible amount of kind of things that we need to implement in the firmware to support the majority of use cases for our bootloader. Now this is somewhat suspiciously familiar. We have our firmware. If we just change a couple of words in that slide, we'll come up with something we've hopefully all seen before. So the idea here is that we're using Linux as our bootloader, or using Linux as a component of our bootloader. We have a lot of existing code, a lot of code that is hopefully quite high quality, and the idea here is we can use the stuff that's already been done to implement the bootloading phase of our machine bring up and deployment. So if we use Linux as bootloader, we get good hardware support. I guess the assumption here is that if your device, if you're using your device in the kind of regular operation of the system, Linux will have support for that device. So therefore, anything you might want to boot off, Linux will support that device. So we might as well use the drivers in Linux to do that. We also get a good amount of memory management. Generally, firmware is all running in the single address space, usually real mode. When we're using Linux as our bootloader, we can have that separation that we get with separate processes, separate address spaces, and whatnot. Linux itself is well tested. We have the hardware support has been through quite a lot of testing. Sometimes not as much as we like, but it is fairly well tested. And we'll probably find that the testing that Linux gets on its device drivers and the block layers and that sort of thing is used, it is spending a lot more time running on your machine than any firmware will ever be, or any firmware boot services will be. So it will receive more attention of testing and it'll be higher quality code. And very importantly, the code for the bootloader, or the drivers and everything is available. We can hack on them, we can fix bugs, we can implement our crazy things, and we can play with the bits we need to play with to implement the kind of boot process that we want to implement. So we've got the loading part sorted out. We know that we can load files in Linux. If not, we're in a bit of trouble. But we can load files, we can do that sort of thing. That was one of our features, required features of bootloader. We cover some of the, one of the other features we need is the execution of that kernel. Now, we use a facility called kexec. You might already be familiar with it, but just a quick overview. So we have a kernel that's running on our machine. In this case, this will be the kernel we're using for our bootloader. We have a system call called kexec load. And now this, you pass it a list of pointers to bits of memory that are your kernel, and it will load that kernel B, the second one, into a reasonable chunk of memory, and then we can then execute that second kernel using this standard reboot system call with a magic value for the argument. So in that case, the execution is handed over to kernel B. Kernel A is still in memory, but not actually doing anything. Kernel B is then free to free up any of the memory or resources used by that initial kernel. And now we have just your second kernel running on the machine, hopefully in a fairly clean environment, just like you'd booted it directly. So that's the kexec facility, and that's how we hand over execution in a Linux-based bootloader. So now sort of enough abstract talk. Let's go into some of the details of Petitboot. So we had the three things: the loading, the execution, and the user interaction. This is how we do it in Petitboot. So Petitboot is runs all completely in user space. I guess Petitboot is the component that does the bootloady bits. We also have a Petitboot-based firmware would be Petitboot plus the kernel and the other sort of things that we need to have a complete running system. But anyway, so we have Petitboot. We have it listens to hot plug events. So as your machine is booting, devices will be discovered by the hot plug infrastructure. and Petitboot receives notifications those devices are available. We then look on those devices for any configurations that might indicate there's an OS installed. So basically we'll look for existing bootloader configurations to say, here's your kernel, here's your RAM disk, and here are your kernel arguments. And that we then extract a boot option from that configuration. Depending on our environment, we'll typically execute that kernel, the one that we've loaded, we'll find a kernel from that boot option that we're supposed to load it, and then kexec into that kernel. And of course, we have some method of user interaction to cover that. So that's kind of our three features of bootloader that that's the way we implement in Petitboot. So the structure of Petitboot, everyone likes diagrams, is kind of a really lightweight client-server kind of thing. We just talk over a single socket. We have this Discover server, which is responsible for receiving the notifications of new devices and kind of collating all that and acting as basically a database of the boot options that are available on the machine. Very lightweight. I mean, just sort of linked list, nothing serious database style here. And we spawn a UI client on anything that a user might be interacting with. So, for example, a serial port, a GPU, or whatever method a user might be interacting with that machine. We spawn a separate process to handle client interactions over that device. So the basic flow, we have udev hot plug events coming into our Discover server. We use libudev, but it's very lightweight. So when we see a suitable device that might contain some kind of boot option, we run it through, we notify the parsers. So we have a set of parsers in the server code, and so we have one for grub, we have one for Pixie, we have one for yarboot, and I think we have a kboot one, but that's not often used. So we have these parsers. The parsers are notified there's a new block device, go and find if there's a grub config on it, and then extract the boot options from that grub config. Anything that it does find, it then passes on to the UI client saying, here are the available boot options, and as they come in, those UIs will hopefully update a list on the screen so you can see what's now available to boot from. So let's say a user comes along and is sitting on a serial port, is interacting with Petitboot, and then sees a boot option and says, I want to boot that one. Just a small message is sent from the UI back to the server to say, boot this option here. And that's kind of it. Then the Discover server runs kexec, and we're happily running our new kernel. So rather than just pictures, I'll do a bit of a demo. I'm going to see that. So what I'm going to do here is start a virtual machine that uses the Petitboot bootloader. The virtual machine is just QEMU emulating a PowerPC system. Nothing about Petitboot is architecture specific because it's just a user-space process. But because we work on PowerPC, that's what I'm demoing here. In this case, we've got a Debian installer ISO that will be attached to that virtual machine. So my script here just runs QEMU with all the right arguments and sets things up correctly. So we start it. And here we're just getting the output from the virtual serial port onto our terminal here. So we've got our firmware booting. We've now got our kernel D message coming out. Remember, this is our lightweight kernel built into a Petitboot system. And then we're in hit user space, and now we're running Petitboot. So it's discovered a bunch of options on the Debian ISO. I'm just going to interrupt this boot process. As you can see, we had that countdown down the bottom saying that if we didn't select an option, it was going to boot the Debian default install. So this is our UI. We've got some information about the system up here and the boot options that we've found on that block device. Just going to. This is looking at as you can see, we've still got a little bit of tweaks to do on the UI with ISOs, but this is showing the detail of that first boot option. We're using this VDA device. We found an image and an ERD on that, and that's what would be booting if we were to select that option. If we go back, we also have a little system information panel just shows some information about the system. The main purpose of this is so we can find out some identity of the system, find out which MAC addresses it has and whatnot. We also have a tiny little configuration interface. This is mainly to allow an easy way to configure the network and that sort of thing of the machine. It does nothing special. All it does is the same as any of the ifconfig or whatnot tools, but saves that state into persistent storage in the machine. So the next time you boot, you'll have the same network settings and whatnot. At the moment, this is all the defaults. We're defaulting to DHCP in every interface we find, and time out after 10 seconds if we don't find, if there's no user interaction. So we'll just cancel this. As I said before, we're using a standard Linux system here. So of course we have a standard Linux shell ready to go. So remember, we're still in the bootloader at this stage. We haven't actually booted our final OS. We're running a tiny Linux system and we have a shell available. So we can do our standard kind of things. Actually, I'll give you some details about our Petitboot. This is our Discover server here, which I mentioned. This is listening to all the hot plug events, discovering any boot options that are available. And we have a UI running here. Now I've exited the UI. This UI process is actually one listening on a separate serial port. So this virtual machine has two serial ports. One of the UIs is still running, the other one's exited because we're now in the shell on the serial port. But that same client-server model where we have an extra process for our, or one process per serial port. Also see our DHCP client running here. Just running a standard small DHCP client, and that's what we're using to configure the network in Petitboot. We pass a few extra options to allow discovery of boot options, but that's kind of a little too complex for now. We have all the standard bits here. Interestingly, we should be able to. So we have wget. We have all our cool tools, so we can actually, in our bootloader here. Remember, we're still in the bootloader. We can do all sorts of things you would expect from a Linux system. If I actually notice here, we've mounted our Debian ISO into the file system. We have a small tree of devices that we mount. Anything we discover we'll mount under this var Petitboot mount directory. And this is just the device we found from that we've discovered through hotplug. So the hotplug system will trigger mounts of everything, read-only mounts, so that we don't alter anything inadvertently. And then Petitboot would have read the yarboot config from this ISO, and then each one of these would have generated a boot option that we saw back in our UI here. So let's do what we expect to do with the bootloader and actually boot something. So we've shut the Petitboot kernel down. We did that reboot system call, and now we're running the Debian kernel. So this is just producing the dmessage output as you'd expect. And this kernel was again discovered from the Debian ISO, and we're doing the standard Debian bits. We are running virtually here, fully emulated on my laptop, and then we have the Debian install. So that's Petitboot. I always wondered why there's a C language option here. I don't know anyone who speaks C natively. Gets through.
Have you filed that bug report already?
No. Cool. So that's Petitboot. So what we've sort of covered here so far is kind of the basic bootloader functionality. Things that you expect from a bootloader, things that aren't that exciting. We've just managed to boot a kernel. What I did promise in the title of this talk was interesting things. So we find that the standard Linux environment that we get from Petitboot gives us some cool opportunities. As you saw, I did that wget. Not many bootloaders let you wget directly from your bootloader environment. So some of the things that have come out of that, I guess the disclaimer here is these are ideas, they may not be good ideas. So just keep that in mind. One actual thing that we've found is having a Linux system in your bootloader is actually really helpful for debug. When we're doing bring up, we don't need to worry about having an operating system to boot to. We can just kind of have our operating system right here. And if there's any problems with a production system, if it hasn't booted, if it hasn't found a a grub config or whatnot, we're a little bit stuck in terms of we don't have the tools we usually need to fix the problem. But in this case, we have we have VI in there. We have a small Linux userspace where we can use VI, for example, to edit our bootloader config or fix up any configuration files that aren't right, or maybe fix the FS tab in the operating system we want to boot. So we have that facility to either fix bootloader configuration or fix operating system configuration that may be preventing us from booting. So that's one kind of advantage that we didn't really predict when we were writing this thing, but it's been kind of handy. One of the areas that we sort of work in a bit is the cluster environment, and quite a few folks that I've spoken to have issues with using typically a netboot, because you don't want to keep 10,000 kernels one on each of your machines, or 10,000 machines. So you want a netboot. And one issue that's been coming up a bit is using TFTP to network. You have a very simple network stack, so you want to use a very simple protocol, TFTP, to transfer your boot files from your machine. But when you're booting 10,000 machines at once, you'll see lost packets, you'll see retransmits, you'll see lots of things that kind of make UDP not quite the best option for the job here. So if we could use something TCP-based, it would be good. EFI does have support, or some firmwares do have support for FTP, but why not do something like HTTP boot? We had that wget before. You can specify HTTP URLs in your bootloader config. Petitboot will read those and allow you to boot straight from an HTTP server. Security considerations aside, yeah, it's great. We don't see a lot of support for HTTP in bootloaders, probably because it's not a great idea to do real mode string parsing in C in your bootloader. So here, because we're using standard Linux tools, we're using wget, we're using things that have been tested quite a bit, and we use things that have been out in the environment. We're kind of a bit more confident about using our userspace HTTP client without too much concern about running that in the bootloader. So that's been kind of cool. So heading further into the maybe not so great an idea territory, but still crazy, why don't we have a web app that serves our kernels to us? Rather than having to worry about reconfiguring Pixie or getting a netboot systems all running, why don't we just have one HTTP app, or sorry, one web app that serves kernels to whatever machines are requesting them. So we can do a bit of dynamic things there. And typically, I guess you'd implement this by having a database and some sort of web app that queries your database and finds out what kernel is supposed to boot, serves that kernel back to the to your machine, and then boots that. Why not go one step further and take out the web app and make your servers configure themselves? That you could have your database client libraries directly on your bootloader and doing queries to SQL. I mean, like I said, not necessarily a good idea, but we can still do this. This is sort of the flexibility we get by using a standard Linux system to boot nodes in your cluster. One other thing I mentioned in the abstract was BitTorrent. There were some folks that were trying to sort of shoehorn BitTorrent into their cluster boot environment. You've got 10,000 whatever machines booting at once. Why don't you save some network bandwidth increase some reliability by having BitTorrent used to serve your kernels around the cluster? Now, perhaps that's a little too heavyweight. We might have concerns about running BitTorrent in our bootloader. Maybe we could experiment with our own kind of multicast protocol. Maybe there's some work we want to do in experimentation with different multicast protocols, booting 10,000 machines at once. Why don't you share that traffic around? So again, we're using a standard Linux environment to do our booting. Pretty easy to develop for. I'm sure most of you guys have done some work on user space programs. You know how to program for Petitboot, so that's great. And it's pretty simple to add little bits in. A bit of history on Petitboot now. It's originally written when a few of us in the team were working on the Linux on PS3 bits. So we have a PS3. It supports Linux. There's about a 4 megabytes bin of flash that we had. So we have 4 megabytes of flash to put our bootloader in. Minus X. Increasingly growing X all the time, wasn't it? But anyway, so we had a little area to put our bootloader in. And rather than writing a bootloader script from scratch for PS3, we wrote Petitboot. Again, similar style, very similar to how it is today. The UI is our server, structure. And using that, because we had generally if you're booting your PS3, you have a TV there, you have maybe a keyboard, maybe something over Bluetooth. We have the basically specific requirements we want out of a UI. You want to be able to see it from your couch and that sort of thing. So rather than using a text console, we had this nice little frame buffer display for our bootloader. Again, everything is still running in the bootloader. We haven't hit our final OS yet. This is just the way you would select the machine you wanted to boot from that stage. I'm not sure why we came up with the idea of Igloo OS, but I think I had an icon and we needed something to go with that. So. But yeah, this is one of our test boots for Linux and PS3. Now, implementing something like this from scratch in a real mode bootloader would be a giant pain. So we used some of the existing graphics drawing libraries that Keith Packard wrote called Twin. That combined with just some munging of input layer stuff, and we had ourselves a nice frame buffer bootloader using existing bits of code and not a whole lot of plumbing. So that was really good. One of the advantages again of using a vanilla user space for our bootloader. We also have options for remote access. There's nothing stopping us from putting an SSH server, maybe apart from Sanity, on our bootloader. So it's entirely possible to put an SSH server. You probably use it for more debug and more than just automated management tasks, but it's definitely possible. We also have potential features of security and authentication. We have some standard bits available to us, things like GPG and OpenSSL, which we can use to authenticate the kernel and the bootloader, or the kernel and the RAM disk, and the bits that we're jumping into from Petitboot. One of the challenges here, though, is why it isn't implemented already, is defining where the root of that trust for any sort of authentication is. EFI has quite a few definitions about how that's done. I'm not sure if we want to follow the same way or do something very similar to that, but we have all the tools here to implement proper authenticated boot, as long as we can sort of share some sort of predefined root of trust. Now, I've covered, I guess, a few potentially crazy things. Hopefully there's some other ideas out there in the crowd. And to that end, I think I'd like to cover a bit of development of Petitboot and just a brief section on how things work at the moment and how you can start playing with it. So Petitboot uses all the good stuff, userspace, C, Git. It's entirely possible to add other things into the Petitboot environment, but the Discover server and the processes and the UIs are all C at the moment. But again, because we're in user space, we could do Python, we could do Perl, we could do whatever. Yes, Ben.
Do we put somewhere, or should we put somewhere a Bridle script that we can use?
I have my tree up. I haven't announced it very widely, so it is possible to build it. So Ben, so the question was, do we have a builder script up? I wasn't going to mention builder until this slide, but so as I said, we're in user space. We're in C. When you compile Petitboot, you get a user space binary. Now you can't boot that, of course, because it's a user space binary. So we need to combine the Petitboot user space with a libc, with the libraries we need for Petitboot, with UDEV, with a DHCP client, that sort of thing, into something that can be booted by the hardware. So we use Buildroot to do that, which takes various components, and an excellent project for building embedded user space bits. I think there was a talk at LCA, but it's probably already been yesterday. Yep. But so we use Buildroot to construct out of Petitboot a couple of other projects, a init ramfs, and I'm amazed how small you can get these things with Buildroot. We've got, I think, our bootloader in 2.1 megabytes at the moment, and that's with no kind of work on trimming things down. So out of the box, 2.1 megabytes for our entire Linux system is great. We added a kernel to that, and then that becomes your bootable OS, which is your bootloader. So I'll give a bit of a quick tour of how we do a Petitboot build. I'll just blow away my.
Move it aside.
Sorry?
Move.
No, that's all right. It's not important. I say that now. Yeah. So here I've just dropped the build tree for Petitboot. And now we're running the standard builder make scripts, which it's only building the Petitboot component. It's only rebuilding the Petitboot component. Standard configure, make, install. Builder it knows how to construct various open source code bases, build them, possibly download the sources, build them, configure them, and then put them into our live file system. So now, out of this, we have we've just built a couple of oh, it's growing a bit today. So this is our rootfs here. So because I had most of the other projects already built in my tree, it didn't rebuild everything. But here we just rebuilt the Petitboot project, constructed our rootfs, and then that's what we use for our init.ramfs when we plug it into our kernel. I can give you the expanded. So that's, contrary to what it says, it is actually, this is our root file system in its expanded form. There is a warning there that it's not, so you don't go and use that directly, but the CPIO is the official format, and this is the expanded version of that. So, sorry?
Would you get any real win from using bzip or LSR?
Yeah, yep.
Repeat the question.
Sorry, the question was, would we get any advantage of using different compression algorithms, so LZMA, bzip, whatever? Yeah, we're just using gzip in this case because it's easy, it's fast.
It's not a huge issue nowadays because when you build a kernel with linux.conf.au, the kernel root file itself, you can specify to compress it with any other support.
Yeah.
So you can use actually the CPI
yeah.
here, and on the kernel build side, just say you want it compressed.
Yeah. So what Ben was saying there is we may as well just use the uncompressed one because when we build that into the kernel, it gets compressed anyway. So and we can select which encryption algorithm, which compression algorithm we want to use for that. This is again a kernel configuration option rather than a builder one. Now, unfortunately, because we're not just doing a single build and test of Petitboot, there's a bit of complexity in the testing cycle. So you write some code, you might update a parser to support some new grub feature, and you want to test that. You don't want to have to go through the entire user space build process, and then build user space build process, then build your kernel and init.ramfs, and then test that and do something. So we do have an in-tree test suite, as most projects should. Where we can test the critical components of Petitboot, sort of the bits that we can separate which don't require everything to be integrated. So at the moment we use this to test things like we've got a list library, we use that, we run those tests in tree. We test all of our parsers, most parsers have quite a few test cases to ensure that we kind of do the right thing when we see various grub configurations or yarboot configurations or whatnot. And that's incredibly easy to run. We just run make check and it runs through all the tests. And one really nice thing about running our tests in tree is that we can, or running our tests in tree for a user space project is we can run them under Valgrind. So we can do our bootloader validation in user space with proper memory checking and proper point of validation and use up to free and all that sort of stuff that Valgrind gives us, we can use to validate our user space bootloader. But that's not always enough. We do want to test some things like when you see a DHCP response from a certain server with these options, we want to make sure that it does the right thing in terms of requesting the kernel resources and whatnot. So we do have some integration tests, and they're implemented as it's an out of tree, just a little Python thing that I've got going that spawns a QEMU virtual machine with a tiny little fake network and a configurable block device configuration. So we can plug, basically each test says put this block device on with this particular grub configuration file in this file name, and then run Petitboot, expect to see that boot option appear in the list of boot options. When you boot it, make sure that it's tried to request the right kernel from that block device. So we can do all these sorts of things by using QEMU using QEMU to sort of handle the virtual boot. Of course, it doesn't test out real hardware behavior. That kind of becomes a more difficult problem, but it's not something that Petitboot really needs to worry about because it is a standard user-space program. We shouldn't need to worry too much about intricacies of hardware. That's all handled by the kernel. We can kind of hand wave that away. Hopefully the kernel works then. So that's kind of the overview of what the development of Petitboot looks like. It's all done in one Git tree on git.kernel.org. I won't put the full URL because it'll take up the entire slide, but git.kernel.org. The project itself is maintained by a colleague in open source, Jeff Levant. He and I do most of the commits, but there's a few other contributors as well, including Ben who's here. So that's kind of Petitboot. Any questions? Cool. Start at the front.
IPv6
Yes. It's something I'm working on once we've kind of done our initial release. Sorry, IPv6 handling. It's definitely, it shouldn't be too much trouble. It just means that we need to make sure that we handle the addresses correctly in our parser. But other than that, shouldn't be a whole lot of work. Maybe there'll be some difficulties around DHCP for IPv6 and Slack and whatnot, but I don't imagine it to be much, again, because we're just using user-space bits. So, yes, thank you. Yes?
How easy is it to build a Petitboot image with different drivers in it for specific hardware?
Oh, simple. It's just a matter of configuring a kernel to have those drivers. So,
separate packages are in the usual distro trees and whatnot.
Okay, so the question was how you would build with, how easy it is to include different drivers in the Petitboot system. And yeah, I think because when Petitboot itself doesn't care about the kernel it's running on, as long as the kernel can run standard user-space processes, Petitboot itself doesn't mind. Doing the infrastructure to allow that is more a product of your build process rather than your development process, that's all. So as long as you can build a kernel with that, you're fine. Yes?
How does it compare to Coreboot?
How does it compare to Coreboot? I haven't played a lot with Coreboot, so not quite sure. Can you give me a two-sentence background?
No, I was asking. That's why I was asking.
Okay. Nope. Sorry, at the back here?
So if there's a new linux like operating screen
So the question was, say you want to upgrade the kernel that Petitboot is using, or the Petitboot system, is that easy to do? Now that's kind of brings about an interesting problem, is that if we can boot the Petitboot kernel, why don't we just boot straight into your operating system? Now, I guess the answer to that is more about management. You want to be able to have some way to select which boot options are available and that sort of thing. So, but of course, if there are serious bugs in your kernel, you want to upgrade the Petitboot thing as well. Now, I imagine a system that implements the Petitboot bootloader, that includes the Petitboot bootloader, will have a very light firmware that includes maybe one driver to pull your Petitboot kernel off something like Flash. So how easy that is depends on the system that it's on. For experimentation about this, I would assume that one way you could sort of start using Petitboot on your own system is to build it as an EFI stub, and then have your EFI firmware boot straight into Petitboot, and then you get the full Petitboot system from that. But again, it will depend on the system and how it works. Yes?
Can I run this on my 40 bucks mainboard? It's really cheap and doesn't probably have a lot of ND render.
So you can boot it just as a standard Linux system. Sorry, repeat the question. Can you boot this on your 40 bucks main white box system with not much NVRAM? You don't have to put it in NVRAM. You could put it on disk. You're kind of defeating the purpose of Petitboot at that stage because you're booting a kernel in. But it's possible to put it somewhere and boot it from, put it on your disk or whatever. It's probably not going to be the optimal situation for that for your existing BIOS-based machine, because you can just you can boot your operating system, whatever. But if you want the flexibility in the feature set that Petitboot gives you, you can just boot it like your normal operating system. And then you have sort of a 3-stage process rather than a 2-one, but that's fine. The actual resources of the system won't matter at all. It's a tiny kernel. It's not performance sensitive at the moment, unless you have large amounts of disks, which we're looking at the moment. Matthew.
So how reliable have you found kexec in terms of functionality on top?
So the question was, how reliable have I found kexec? Do you want the Anton answer? Or so what we're actually using for the testing I've been doing is a very, very stripped down version of the kexec user space. Are you talking about the user space or the kernel? So what we can do with Petitboot is boot Petitboot. So one of the tests I've done is set up a boot option on our device that just sort of re-execs the same kernel and init runfs. Now, at the moment, I think we get around 1,000 boots until it stops working. But it stops working because of the ATI driver, not kexec. So we have other fruit there that is lower hanging than kexec, which is really nice. I think, and we can sort of work on those driver issues and hopefully get that fixed. But I haven't actually seen any reliability problems at all with the testing we've been doing with kexec, which is nice.
Are you just testing it in VMs or on actual hardware?
Both. Yep.
With different
Sorry, the question was, have we testing on VMs and actual hardware? Yes, yeah, both. And sorry, the follow-up?
And with different kernels, or does kexec into the same kernel?
So the question was with different kernels or kexec into the same kernel. The kexec I've been doing has been loading a new kernel over the network and then booting that. So it's a separate file, but it's the same binary.
Right.
And yeah, so we're not doing the trick of booting back into the same thing. But yeah.
The problem fundamentally in terms of reliability is drivers. There are a number of drivers who don't shut down properly on kexec and leave the device in a bad state.
Yeah,
in our case, we've been basically fixing them one by one because we also deal with servers that need a limited set of devices that support on those machines. It's doable. But yes, it is probably the #1 reliability issue we have with kexec. Drivers basically crapping out or leaving the device in a bad state. And then after the next kernel doesn't manage to initialize it.
Yeah. Yeah, I mean, the ATI problem I saw was, I don't think that was kexec related. I think it was, I can't say really, but yeah, it is also a good test of drivers and their shutdown methods and that sort of thing. Yeah. So I guess to expand on that, the issue with drivers is that if you're kexecing your machine and you have some PCI device, for example, doing a DMA into somewhere in memory, your new kernel might be using that for something completely different. So there are some classes of problems where a device is still running and has written over something that we need to use in our new kernel. Yes?
I have 2 questions. You might be able to answer them with one answer. De-encrypt for your kernel, is that included already? And the other question is, before I hit enter on my laptop, what's going to happen after the apt-get install Petitboot? Or rather, what do I have to do to make it work?
So because you've got your finger over the enter key, I'll answer the second one first. So the question was, what happens if I run apt-get install Petitboot on my laptop? Nothing. So that will install the user space bit of Petitboot. It won't replace your bootloader or anything like that. You'll have a binary that implements the Petitboot Discover server and the UIs. It won't do any sort of thing. I don't like any change to system configuration. And you'll probably get some really old code too. So,
but then it's very unstable.
the packaging hasn't been updated for quite a while. So.
Yeah, but then I would use the user space to install it onto a disk or onto NVRAM.
Yeah. Exactly right. Well, no, that still wouldn't be a bootable image. That would be the user space bits of Petitboot, which would then need to wrap up into a bootable image. So the Debian infrastructure, not many of the packaging infrastructures will support building an entire system into a single package. So you'd really need to use something like Builderit to get the Petitboot sources and build it up into a full running system. So that I haven't looked at the Debian package myself, but I assume that they haven't provided the init runfs and all the bits you need to get Petitboot running. And the first part of the question? De-encrypt? Yeah, do we support de-encrypt? So I have a cut down version of the MD Atom bits. I don't think I've put dencrypt in my builds. There's nothing stopping you from using bittorrent and including the dencrypt bits. You'd also have to put, I'm assuming you need some sort of key on there in advance and whatnot, or at least have to type in, yeah. So definitely possible. We have all the bits required, like it's a normal Linux system. There's no reason you couldn't build a Petitboot image with whatever you need to boot installed. One at the back, have time. Last question?
Just quickly, is it possible to boot kernels or images that don't support kexec?
So the question was, is it possible to boot kernels that don't support kexec? Yes. The fact that your second kernel doesn't support kexec has no bearing on how it goes. As long as we can...
the first kernel does.
Well, yeah, it's up to the first kernel whether or not we can kexec.
So you could even boot, say, like something really different, like Windows or something like that?
As long as the kexec tools can parse it and do that sort of thing. For my tests, I wrote basically a tiny shim that prints out, it's basically a tiny kernel that prints out, yes, we kexec'd, and that doesn't support kexec, and it boots fine. So, cool. If there's any other questions or anything, let me know after the talk. I'll be around for the rest of the week. Be happy to chat about it. And thank you all.
Thank you.